All righty then. All right, we should be good to go. All right, don't mind the stuff on the board. We were just doing some stuff and things earlier. All right, we'll let folks roll on in, seeing as I'm totally, absolutely late, but that is fine. That's fine. What we're going to be doing today is we're going to be going across the ingredients of reality. What are the ingredients of reality? I'm glad that nobody asked. Okay, that was a lie. People occasionally ask, and you'll get all these different random things, all these different answers and everything. All right, so I'll take the time, let the folks roll in. We'll wipe off the board. Maybe I'll eat a donut here in a minute. Maybe we'll get a little bit of a free mukbang, as, as the kids call it. As we're doing our different stuff. I took a picture. So, all right. But here's the interesting thing, and I don't hear enough folks talk about this. They'll talk about the constants of nature. I know Professor Unziger likes to talk about it's like, oh, you get C, you got H bar, you get the fine structure constant, you get the Newtonian gravitational constant, whatever that actually is. And you'll hear it expressed in those forms as constants of nature. Okay, but there are other constants that we can get out from actually just doing the calculations. So we actually have, you can reduce them down to five bases of reality. So we have five dimensional ingredients. I can spell. Yeah. Okay. Five-dimensional ingredients. It's like, how do you remember that? Oh, we tend to have five senses. It's, what is it? Sight, hearing, touch, smell. I'm missing one. Taste. Yes, there we go. And then they seem to be interplaying with each other because it's like, well, if you can't really smell, taste isn't as good. And it's very interesting because, especially with things like charge, which we were talking about a little bit the other day, uh, charge is very interesting because a lot of the times, and this is one of the things that confused me even on Wolfram Alpha, it's charge. Just do Q here for charge because that's what we use for charge. All right, charge is equal to time multiplied by current. That's that's a very interesting thing, but these can be computationally reduced into this guy. Computational reducibility strikes again. Okay. So why am I talking about this? Because with all the constants in nature that we have, about approximately 288, which that's a fantastical discussion in itself, but we got to build up to it. We got to build up, have our building blocks. So, like in Minecraft, we're going to have some building blocks. What are our building blocks? Our building blocks are time. We make time a little bit more. There we go. Emboldened. Time. Space. Duh. You get charge. I think we were just going over there. Charge, mass, and temperature. So, like Captain Planet, when those ingredients combine, not all at one time, because coincidentally, we never have more than four expressed at any one time. Yes, I'm using time interchangeably because within all the constants of nature, you might have time and space. Space is actually length. We got a notion of length here, but it could be one dimensional. All right, you got this much space. It could be two dimensional. All right, I got a square area or something, or maybe a circle within the square. Maybe we're squaring the circle. That's another interesting conversation. And then if we add an additional dimension to it, our standard cube thing, we cube length, we get a cube. I know. Imagine my shock. But those things, like if you take distance of length. You take length, you divide it by time, small t. That's very important because if you do big T, you're going to be about 76 orders of magnitude off. Drove me crazy. And then I realized, oh, user error. Oh, hey, Ernesto. Good to see you, my friend. Thank you for joining. Okay, length divided by time. All right. And if we did L sub P, T sub P, we get, I'm going to claim approximately C. That's generally how we think about it. I'm saying approximately just because in-house here, we believe there's actually a geometric action going on about 7 decimal places in. Don't worry. It appears to be a minimal action, or at least on the minimal 3 manifold. Okay. So we got time, we got length. We'll go over and do a little bit more here. We got time. So we have these ingredients. These ingredients make up the constants of nature. What are our bases for these? Time. Oh, T sub P, blank time. Space is length. L sub P for length. Charge. Q sub P for Planck charge. Mass. M sub P for Planck mass. And temperature, big T sub P for the Planck temperature. Okay. There are only 5. It's kind of like the Platonic solids. Now, I'm not saying they play an integral role in what's going on. Maybe they do. Maybe they're part of reality. Is it this exact reality in itself? I don't know. Maybe we need to go up a dimension. Now, that is sheer speculation on my. Oh, hey, Dan. Yes, yes. No, this is a good talk. This is a good. See, I was getting ready to do the actual thing, and then I realized, well, the camera, the angle, and everything, it wasn't as good, so we might as well do it again. And if I actually want to communicate this with other human beings across the world, because this is something I haven't heard anybody argue about, and actually going through and doing the calculations, you can see it's like, well, there are only 5-dimensional bases that you actually really need. Yeah, you can try just doing C, doing this, doing that. But then you realize it's like, all right, well, we got C here. What if we wanted to do big G, big G? All right, as far as we know, the dimensions, again, I'm going to do approximately because there is other stuff going on. Big G, it's, well, we're talking spatially in 3 dimensions as we know it. So we need a length factor. So we do Planck length, we cube it. So we get our spatial area over here. And then we put Planck mass here. And then we have the Planck time, T sub P, and that's squared. Why is it squared? Because that gives us uh, the the form of acceleration. Because otherwise, it would just be doing a thing. It would just be doing a 3-dimensional thing. With this, as long as you have time squared there, it's a form of acceleration. Okay, we got okay. Hold on, I need to do a real quick tangent because this is really fun. Might actually make this into a short because we take. I'll share with the class here because acceleration is very interesting, and actually, I probably should clip out one of Professor Sean Carroll's things because he actually says it in a very interesting way. Okay, so you do 1 over. Let's do meters squared. Hold on. I need to do time seconds squared. Let me do that. That should actually make it correct. Okay. So we're getting vorticity affection. That's a very interesting thing for other reasons. We'll get into that. Let's do meters over seconds squared. This should give us, okay, acceleration. We're in the right dimensional form right now. But so Facundo, yes, we're talking about within charge, we're talking electric charge, which is a factor of time times current, which if you break it down, you can actually computationally reduce that into charge. Okay, so right now we've got a unit of length and then divided by a unit of time squared. That gives us acceleration. What if we cube seconds? What would happen? Oh, I think you guys are going to like this. Why? Because we get jerk. The excuse me, the third power of length is literally called jerk. Yeah, yeah. Oh no, no, yeah. It labels them all. Okay, jerk. We got jerks here. Okay, jerk is literally why. Now, if you've ever accelerated really fast, it's gonna feel like you're gonna jerk back. Okay. What happens if we raise it to the fourth power? Here's where we get into it. We get snap. We get snap. It's like, oh, you're feeling the snap. It's like, okay, to the fourth. What happens if we go to the fifth power? If we go to the fifth power while doing our same form that we're using for acceleration, we get crackle. Wait a second. Wait a second. Hold on. Is anyone else detecting a pattern here? We got jerks, then we got snap, we got crackle. Y'all got three guesses on what the sixth power in this form is. What is it, my friends? They wouldn't actually do it. Yes, it's pop. It is literally pop. The last three derivatives of acceleration, I think it stops here. I don't think there are any name things. You could raise it to the seventh power. There's no standard name quantities, but yes, the the fourth, the yes, the fourth through the sixth power of a length divided by a unit of time are snap, crackle, and pop. Oh, that's interesting. We got guest monk Thad here. Yeah, yeah. Hmm. Yeah, right. Yeah, yeah, yeah. Hmm. Oh, that's that's very interesting. I guess seven is a lucky number there. But tangent, tangent aside, uh, see that's just a very fun little interesting thing. And yes, they name them after the Keebler elves. It's at least according to the lore I got, because I mean, statistically, who's going to be like, well, let's call it snap, crackle, and pop. Are those the first things that come to mind? Snap, you can justify because it's our more violent motion at that point. I'm not saying somebody was like, snap. Oh, we should call the next one's crackle and pop, and just this is why I stand by physicists. Yes, yes, yes. So I'm just like, all right. So physicists are just some of the best trolls in existence, in my opinion. There. Uh that's hey K Shell. It's Dan says hi, Thad. Yeah, that's his hi. But yeah, no, we yeah, there's a lot of very interesting stuff coming down the pipeline very soon. So okay, we had our snap, crackle, and pop there. Okay. What was I talking about? Oh, yeah, I was talking about big G. Because basically, you have big G, you can use the constants, but then you see it's like, wait a second. Length, length, mass, mass, time, time. Wait, C is length, time. Huh. The moral of the story, or at least the point I'm trying to communicate, is that you only need five dimensions of measure to construct the constants of nature as we know them. Well, that's the thing. No, but before that had said that to me, I'm sitting there. I'm just like, okay, I just kind of took his word for it. I'm like, oh, okay. And I just go through. And then once you start doing the calculations and you're like, oh, but we have angle here. It's like, well, angle doesn't have a notion unless you relate it to two lengths. And then it's like, oh, well, it's current. And then current is time times uh, no, it's charge divide by time, I believe, right there. Because that's the one that always confuses me because Wolfram likes to come back with current. So every time you see current, you know there's also going to be some time going in there. And if you have 2 units of time and 2 units of current, well, that's just 2 units of charge because you can computationally reduce it into simpler notation and you can limit the ingredients. So, in order to get reality as we know it, we have 5 dimensional ingredients. That's pretty cool. I can count the 5. Now, I'm not trying to take away from an infinite dimensional Hilbert space, but hey, don't get me wrong. Mathematics is beautiful. Mathematics is amazing. But at least according to standard calculations, the Hilbert space in which we live is actually e raised to the 2 pi dimensions. Uh, no, no, like, seriously, it is the actual calculation. Uh, do I do that now? No, that's a separate conversation. But oh, we got Keishal and Eric. Yes, temperature thought. So, well, it's an emergent property of velocity. As far as I understand it, I believe Professor Feynman said something along the lines: "Is temperature is a measure of the jiggliness of atoms, uh, or basically the vibrational. I like oscillational because if you oscillate, because waves oscillate, they don't necessarily vibrate. I feel like oscillation is a more encompassing term because oscillation, yeah, it's a vibration, but your waves can also oscillate. So if your waves are oscillating, you can encompass more. Um, Perhaps vibration is a better word for it, but yeah, it's a measure of, I believe, can yeah. So yeah, we got. See, that's very interesting, and this is where our good friend Ludwig Boltzmann comes in. Because with Boltzmann's constant, dude was like so brilliant that he managed to figure this stuff out, and he was arguing strongly for atoms, and a lot of folks, I think, they were anti-atomists and stuff at the time. And unfortunately, he got made fun of, ridiculed for all different reasons. Fortunately, he ended up taking his own life, sadly. But now the work, it's like we come around years later, and it's like, oh my God, dude, man was a genius because he was able to figure this stuff out in what, like the late 1800s or something. So that's Dan is commenting. Temperature is a resonance of the manifold. Hmm, it's an interesting thing to ponder right there. But generally, it's the way I see it. And okay, I'm going to give a shout out to Casey just because he got in my mind jogging about some other things too. But generally, to my understanding, we'll get rid of our circle and the cube right over there. But as far as things going on, all right, let's say you get your particle. Imagine your standard billiard ball or your balanced manifold, whatever configuration is going on. All right, this thing is vibrating. We're going to vibrate by, all right, it's got this little vibration. If it has energy, it needs to maintain some form of a balance. So you're going to end up having, again, I'm not a chemist or anything, but as far as I understand, if that has a bunch of kinematic energy, it might need to shed that because you might have some electron. Again, I'm just going to do the traditional electron orbital. If it needs to go up to a higher orbital and then it ends up going back down, it's going to emit a photon. And we have our standard. Oh, yep, yep. Oh, photon goes out this way. Does it go out that way? Is it more of a spherical surface that's going out like this? I don't know. It depends on who you ask. Is it a continuous wave front of more circles and more circles? I don't know. We can just go with the traditional, widely accepted right now version of a photon. Okay. Atom jiggles, it gets energy, it needs to give it off, and then it gives off a photon. And those photons, if we measure enough of them, we're going to get a notion of temperature. Because even what was it? I believe it was the solar. We had a satellite. We had an instrument that was flying like through the corona of the sun, and all of a sudden we're getting measured. Oh, we detected a temperature of 10 million degrees. Really? Yes, it was a single photon. Now, you have a 10 million degree photon hit you. It's probably not good biologically. It's probably going to wreck some things up. But if it's just a single photon, you might be okay. If that temperature is 10 million degrees average within about a meter and 2 meters high or so, I will be vaporized. Like, I ain't gonna be here. It's gone. Why? Because that's really hot. And it's kind of, again, I'm not a doctor or traditionally trained physicist nor mathematician, but my whole thing is I'm like, all right, uh, int- intensity, exposure time, amount, something like that. I'd worked with a gentleman. He had originally studied chemical engineering before he became an attorney up at the University of Burlington, and he told me it's like, well, yeah, we're exposed to things that are deadly as human beings all the time, but like, okay, yeah, there's some arsenic in the water. Now, if it's like 10 trillionths of a part per, like if it's 1 part per trillions and trillions, I'm not a doctor. You'll probably be okay. If you have a high concentration, somebody's probably trying to poison you. Um, Either that or maybe there's some old pipes they need to be dealt with. Ignorance before malice. Malice does happen. It's a horrible thing, but I think a lot more in reality can be explained by major oopsies. And we all know people are really good at owing up to their major oopsies. It's not like they're going to gaslight forever until you forget about it. I mean, God, that would be so anti science. Who would do something like that? You're going to need a little bit of root beer. Let's see what everyone's up to. Oh, hey, Rick. Good to see you, my friend. Thank you for joining. All right, Dan is commenting. This is energy expressed in 5 dimensions. Now, we have to be cautious because energy does. If I'm not saying it's wrong, because ultimately it's. I don't think anybody truly knows that. There's probably some people out there that have extraordinarily high approximations, but I don't think everybody is anybody that has all the answers. Now, I could be completely wrong about that, but I think there are some folks that have extraordinarily strong explanatory powers. Some folks will say, "Oh, look at what this person did. It's just numerology." So I'm going to make the claim that numerology is numerology until explains more with less. Um, I think that's a fairly accurate statement. Could be wrong, but it's about being useful. What can it do? Kind of like, what is it? So North Dakota is the show me the money state. I apologize for whoever state I'm completely forgetting the motto of. But it's like, all right, that's fantastic. What does it do for us? Can we explain more with less? Does it explain more with a little bit more, like a lot of bit more? Or can we reduce it to something more fundamental in what we're trying to figure out? Okay. That was a terrible explanation of what it might be. Oh, that's right, energy. Dan, we do need to be careful, just because energy does have a specific definition. Friends there. All right. Because energy is defined as E equals mc squared, yada yada. So basically, we need some notion of mass. So we can do uh, mass. Let's just use Planck units for ones, just because it'll, rather than having to translate back and forth, and this is just kind of how it's coded in my head right now. So we'll do eb sub p, and then we multiply it by c squared, which could be approximately, again, because I think we'll get into it tomorrow about why 7 significant digits may be so significant for a couple of reasons. And don't forget about inverses, because I know Rick is in the chat, and Rick has stressed this to me, along with John Williamson, God rest his soul, and Thad, that looking at things and just seeing the relationships and how they adjust depending on how you look at them can be quite enlightening. So, okay, so we got Planck mass times squeeze squared, which is approximately the Planck mass times the L sub p Planck length over Planck time. Put the brackets. We square the thing like that. Bada boom, bada bing. And this should give us out big E sub p which is the notation for the Planck energy. Yes, we're using the low. In some notation, you'll see sub p might be proton. In this, we're just using it for Planck just because it's, one, it's on Wolfram, and two, we're trying to keep things coherent, because that's the thing. Because you could have whatever numbers, and not all numbers will mix together. You need something coherent, like the metric system, or something maybe like MKS, meters, I think kilometers, seconds, or was it CGS, centimeters, CMS, centimeters, meters. I'm getting that wrong. I know Rick can correct me. Thank you. But you want something that comes together. It's kind of like, all right, well, if you got a car, it's like you can just have a steering wheel, but you have a ran steering wheel. It's not connected to the drive shaft and everything. It's like, I mean, you can pretend to be steering. It's not going to do you any good. And rather than having a vice grip on it, it's like, oh, one something with, I don't know, some amount of surface area you could actually get onto would be better than trying to steer with a pair of vice grip. Now, I say this as somebody that used to be a very bad maintenance person. That occasionally, yes, might there be an optimum tool? Do I have it right now? Is it in my tool chest? Is that something I need to go order? Sometimes you need to make do. Now, not the problem you run into that is if you start using incorrect tools. All right, you have a hammer. They say, well, everything will look like a nail. It's like, you might not want to smash everything with a hammer. I mean, if you're trying to do demolition, that's one thing. But even still, you don't want the building to fall on you. So you want to try to like use some logic and go through. Oh, I almost forgot what I was talking about. It's just that energy does have a very particular definition. So I would be cautious. Um, but then that raises the question of what would be a better word for it? Because I mean, charge. I mean, we use charge literally to like move mass and have it be a form of energy as well. And then space, it's like, well, the vacuum, but apparently there's no true vacuum, apparently has energy in it as well. Uh, that is okay. Oh, that's right. Missouri is the show me state. Wow, wow. I was thousands of kilometers off. All right. Dimensions of freedom. Okay. All right. It's because basically what we're claiming here is if we're going to use some geometric form that has a lot of nice properties, kind of like either a Geeske manifold or its double cover, the hyperbolic figure eight knot. Technically, we're using it the complement of that because it's the first minimal knot that emits a hyperbolic projection, yada 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 stuff terms. Um, but basically, we're trying to get things to balance out, kind of like an accounting scheme. And where was I going with this? Oh yeah, I was checking the rest of the chat. That's also a very good thing. Can we build it? Can we build it? Yes, we can. I like that spirit. Uh, yeah. See, that's the interesting thing. It's like the Planck mass is the math of black hole stuffed in a Planck volume. I mean, that seems to be true, but then again, you look at the formula, like there's a factor of two in there too. Is yeah, yeah, is Planck's energy. Yep, yep, yep. See, yeah, that's where Boltzmann comes in, and that's how we get. There do seem to be certain places where if you try to go from like one constant to another, you do need something like that. So Rick is right in that. What should we do? What was it? Yeah. So if we take like our term here and we go to here, we take the Planck energy. We got the E sub p. So Planck energy, maximum energy for a given thing. I'm going to leave it at that. It's some people might debate on that. Uh, Theoretically, Planck energy, and you got we'll multiply it by. We usually use the notation K sub b for Boltzmann's constant, and then that gives us out big T sub p, which is the Planck temperature. So Boltzmann's constant is very key for us to be able to try to convert, try to be like, all right, if we have this, and we're undergo this, how would it go out? So Boltzmann's constant is Dad was giving it to me before, but that's one of the ones because we may only have five bases as our building blocks, but you can combine them in all different types of ways. That's the thing. Because, all right, five things, you can do 44 different permutations or organize permutations without repeats, but then you can raise them to all different powers and everything too. Uh, yep. Yeah. Oh no, Wikipedia is a fantastic source for this, and you can go through it and get the other things. But no, they go back and forth, and it does seem to be surprisingly accurate. And occasionally, some of their old publications are kind of the links might not always work. But let's go to our friend Boltzmann's constant. Let's bring that up for the class. Boom. Okay, got Boltzmann's constant here. What is that? That's 1.381 times 10 to the negative 23 joules per Kelvin. You're like, what the heck does that mean? That's basically the natural entropy of a 1 over log 2 bit of information. Yeah, that's because it's one natter. That's 1 over log 2 right there. Right. What are our dimensions? All right. We got mass, length, time, and then temperature to the -1. Okay. So if we do this, so if I've learned anything from dimensional analysis, it's a good exercise for me to actually go through. That's why I had Bill on the other day because he actually made me go through. Oh, hold on, let me derp. Scare away with the math. All right. So the Planck energy, what we got? We got Planck uh, mass, length, Planck length squared. That's over lowercase t sub p. Okay, and then we multiply by Boltzmann's constant, which is, oh, is it multiply? Hold on, I need to double check. It's a divide for that. Let's see. Bring this back up. Planck energy. Boltzmann's constant. Okay, so it's Planck's energy divided by Boltzmann's constant. That's what's good. Okay, that makes sense. All right, because I was gonna say, wait a second, I'm getting a mass square term if I do it that way. My error. Okay. So we need to do this. I know, fake news. God, what a new. All right, so we need Planck energy, E sub p, divide by Boltzmann's. Oh God. Oh, that was right. Sorry. All right. K sub b, and it makes me think of it makes me just think of bytes. But then again, well, it's talking about entropy, so maybe those bytes actually have bit into something. I don't think I've ever said that phrase before. All right. Well, I'll give us that. So we do that. We do blah blah blah. We do m sub p blah 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 over uh, L sub p. So we got the Planck length squared. So we got mass times length squared. Dividing. We're getting. We need our time there because that's the speed of light, approximately t sub p. All right. So then we're dividing this out, and Boltzmann's constant is. Let's go back for a second. Because I don't have all these memorized down. Why? Because we have computers and posters, and I don't do this anywhere near enough. Okay. So if we want to do Boltzmann's constant, we do K sub B. All right. Well, that's equal to our dimensions mass. So we do mass. We got length squared. All right. So we get length L sub P squared. All right. And here's where the magic comes in because we divide it by time squared. Oh, wait, this is sounding very familiar. So we got the Planck time squared, and then we've got the Planck temperature built into because it's in the denominator. All right. So if we divide this into that, it's like well, those are going to cancel out. Our mass terms cancel out right there. And we're dividing length. Oh, those length terms cancel out. Oh, and those time terms cancel out. And since we're dividing by this ends up going in the numerator. Bada boom, bada bing. You get the Planck temperature. Embolden it a little bit. There we go. See? And and just to check myself, we'll uh we'll double check with this as well. Because every once in a while I need to do that. So it's like, all right, so yeah, that's what happens when I multiplied them. All right. So we take that thing we were talking about, Planck energy, we divide it by the Boltzmann's constant, blah, blah, blah. We get 1.4168 times 10 to the 32 Kelvin. Wow, that's really hot. What is that approximately? I mean, that is the Planck temperature. Let's just to verify. Planck temp. Probably. Oh, look, it gives us one to all the significant edges, at least for there. We only got 5 right there, which is a very not. Oh, that's what we should actually talk about. Okay, so we're going to be delving into this. We're going to get a little sneak preview for tomorrow. Let me catch up. Uh, well, well, Eric, that's probably an accurate statement. Eric's commenting, and if you build it, they will come, especially if you show them the money. Well, that's yeah. Maybe no color matters except for green. I don't know. I was hoping for a better future. I think we can do a heck of a lot better. Okay. Yep. Yep. All right. Yep. Yep. Okay. LPNT. Yeah. Rick is commenting. Yep. Yep. Planck length and Planck time are minimal values. Yes. And I believe our claim is it appears to be this way. Planck temperature is a maximum value, Planck charge is a maximum value, and the Planck mass is a maximum value. For what? The particular stuff associated with them in some minimal form. Okay. Um, yeah. Yeah. Okay. That. Ooh. QP is minimal charge. Oh. See, this is the crazy thing. My mind always gets confused on that because it's like 10 to the minus 18, but then elementary charge is 10 to the minus 19, and it's like, hmm, because it's about 11.7 times uh, smaller than that charge, or at least, hey, could be totally wrong. Uh, see, the one problem with green though, do not eat a steak dinner in a green room. Like if there's lots of green light, because I think this is just anecdotal story that I heard is they took a football team that was very hungry. They split them up and they did an experiment. They served them both a steak dinner. One half of the team was in the room with like a red light, kind of like red ambient light. Oh, they scarfed up everything. They scarfed. Oh, it was delicious. Part of the team that was in there with a green light, people tried to eat the food, but apparently they got sick. So I'm not sure if that's just, again, I'm not a biologist or anything, if that's just a human thing where if you see meat and you associate with green, it might be rotting and perhaps you do not want to ingest that. So it's very interesting that apparently we can do things and simulate very hungry football players to getting sick just because the light coloring. I don't know. I don't know. Take that as it would. Uh, it's, all right, Rick is commenting. The minimal things act like Lego bricks. I mean, I tend to strongly agree with that. It does seem very Minecrafty. Yeah, it ain't easy being green. That's. I think the Ninja Turtles would agree with you on that one, Rick. Okay, so where we go from here? All right, we have our 5 bases of reality. Let's clean this up a little bit. Let's go to why is this important? Okay. The reason that's important is because we only have so much knowledge. We're computationally limited creatures, so we can only know so much. So that's why we have wonderful tools that we've helped to create, such as, I don't know, the internet, Wikipedia, online journals, archive, public libraries. Heck, YouTube, the sheer fact that some random dude in a monastery in Utah is able to talk to you right now, more or less live, basically communicating at near the speed of light over fiber optic cables going through space, under oceans, and everything. I'd say that's a testament to humanity, my friends. But perhaps I'm an overzealous optimist. I would also acknowledge that. But we only have so much information. And why am I talking about this? Because for these things, yes, I should probably get rid of the. Wait a second, you have a 4 here and you're listing 5 things. Okay, it's no more than 4 expressed. Where I can spell someday. Expressed at any one. No more than 4 expressed at any one time within constants of nature. Constants of nature. Okay. I need to give that caveat because what am I going to say? 5 things aren't happening all at once. No, we're talking about ultimately we want some coherent field configuration that's going to allow us to persist as we do within our realm of reality, or what some people colloquially call universe. I know I make that distinction. Why? Because, well, at least for me, the claim is that our universe, so to speak, is finite in size. It appears to be eternal in time. Does that mean we're going to be around the whole time? That would be nice. I don't know. Perhaps we are going to need to try to go in different directions to maximize our persistence here, but that's deep down. Um, Again, I don't know, but at least if I'm going to claim that, all right, we have a ginormous space. Let's say it's, I don't know, it's probably if we do 1 over the Planck length, LP, we can just do meters over LP. We'll do meters squared. So we're going to get about 10 to the 34 meters. Okay. That's as the radius of our realm. Again, that's a ginormous number. Don't worry, that shouldn't mean really anything to you unless you've spent time doing any of these calculations. It's like ginormous number. Why? We're doing meters squared over a ridiculously small number, 10 to the negative 35. So we're going to get its inverse here. Okay, so that equates out to about 10 to the 8 orders of magnitude larger than what our current observable universe. Okay. So basically, the claim is we live in a place that's much more ginormous than what we have currently observed. If you're going to try to take you're trying to line up some astronomical things and try to trace out a triangle and see if there's curvature. I mean, it's probably going to look flat if we're only measuring like I don't know one one out of like 10 to the eighth of as far as we could see there. And again, we're gonna have to follow the measurements, we have to follow the observations and everything. James Webb is coming back on a frequent and regular basis. Again, it hasn't broken, to my knowledge, the standard cosmological paradigm. The thing that it seems to need to currently be adjusting is our initial galactic formations and everything. And then again, you start seeing, like, at least according to what I have heard from some very smart people, smarter than myself on this internet stuff and things, seem to be going back and finding some really, really dang big, fairly mature galaxies and freaking ginormous, like supermassive black holes. And according
to our calculations, if these things were happening again, to our knowledge, 500 million years after the Big Bang, it's like, wait a second. So what you're saying is those black holes and galaxies have had like another, I don't know, like 12 or 13 billion years continue to grow, get bigger. My friends, there may be some monsters out there. It's, I mean, that'd be crazy if all of a sudden it's like, oh, why are we going? Oh, what's like a rate attractor or something? Maybe it's just some hypermassive black hole. It's what? Oh, hopefully it's not the size of the observable universe or greater than that. Then, oh, that would scare a lot of measurements there. So, no, I'm not saying that's the case. That's just rampant speculation on my part. But there may be some math to actually get it what's going on. It's Rick. I try to be careful with things, and I know it's a lot of times we like saying very bold things. 'Cause there's one thing I learned from sales. It's as long as you as long as you say something with strong confidence and conviction, and you're using your words in a way that feels like you're luring things together, you can literally spout a huge amount of hot garbage. And some people might not know. Some people might occasionally get caught up in a da-na-na-na, cult of personality. That is such a great song. But and again, that can just depend upon, oh, this is the popular thing of the time. We're doing it. The people have their own reasons for supporting different things. But my thing is, it's like, okay, I can speculate all day long, but let's go through the calculations. Let's see what we get. And it's also a lot easier because we now have computational tools, thanks to like Team Wolfram and a lot of other folks that have brought us such great software as Windows and all these other cool things. The Apple, when they don't do an update that breaks everything. But I digress from my other rambling there. Okay, so okay, remembered my point. Let me take another hit of fruit beer. Okay, last bit of caffeine consumed. Let's get to the whole dang point. What's the whole dang point? So we're going to start off and we're going to lead into our discussion for tomorrow. It's why is 7 significant, specifically to the power of 7, and perhaps more so in at least this case right here, 10 to the negative 7, approximately, because we only have so much information. Because let me just bring up the diagram for my own sake here so I don't get these wrong. We'll do the standard colloquial definitions of the Planck constants, and we'll wrap up with there and a question. So start off with Planck time. Planck time. All right, bring it up to the class. Boom. All right, so we got Planck time over here. All right. So Planck time, let me embiggen this. All right. This is what we know is our minimal unit of time. Is there something below that? Again, I'm going to go with the RB Dragons. No idea. So we define the Planck time as equal to, that's geometry, the square root big G, Newtonian gravitational constant, times h bar. That's over the speed of light raised to the 5th power. Why? Well, big G has length to the 3, and then you got area and h. Now let's do the quick little thing here. All right, so big G, LP cubed, MP there, and then TP squared because it's acceleration. So then h bar is MP, it's mass area. So it's got LP squared there, and radion's got 1 time, TP, and then so the 1, TP, haha. And then we got C5, so speed of light, that's LP, over TP. That's all raised to the fifth power. All right. So we're dividing that stuff into that stuff. We add this up. All right, we got 5 lengths. Oh, well, it looks like our lengths cancel out. All right, now we got 5 times as well. Okay, so we've got 1, 2, 3. What am I calculating again? Okay. Okay. Our mass terms are going to cancel out there, and then I do this wrong. H bar is action 1, 2, 3. We're dividing. Blah blah blah. What did I got something wrong here. Oh, we're taking the square root of the thing. Oh, I was gonna say, yeah. So we end up getting we got 2 times left. So we got the time Planck squared. We take the square root of that. We end up getting the Planck time. Okay, I confused myself. That was my error there. Okay. Uh, yeah, it's basically what I did. I'm sorry, because we got length cubed. We got 5 Planck lengths. This was to the fifth power. We cancel out our lengths. Our mass terms cancel out because this is numerator, this is denominator. And then we got 3 Planck times. This will give us 2 Planck times. We take the square root of that as we had on the convention, then we get 1 Planck time. Okay. See, I can actually do some algebra after like 20, 25 years. And it only took a while. But let's see. Liminal. Let's see. Oh, sorry, I missed you. Oh, we got some X comments. We got some I's coming in too. Oh wow. The point of the temperature isn't really fundamental. See, that's the very interesting thing. Temperature does not appear to be the base turtle of reality. What the claim is it's one of the core building blocks that within the constants of nature you can use. Oh, sorry, let me get out of the way. You can use temperature is one of the bases of which you can build up all the other constants in itself here. Basically, time, space, or so length. So time, length, charge, mass, and temperature. It's very interesting. And again, I haven't, outside of that, I hadn't heard it from anyone else. But within those 5-dimensional ingredients, you can construct the constants of nature. Now, maybe for Planck's constant, you need like a 2 pi. So you have like some circle operator going on there. But yeah, I heard it. I'm just kind of like, okay, I just kind of like, oh, well, that's an interesting thing. Is it really true? I don't know. Maybe I'll say it because a smart person told me. And then you actually start doing the calculations and you're like, wait a second, you do only really need 5-dimensional ingredients in order to construct the constants of nature that we have over there on the poster. I should probably start showing those posters and stuff. So, but thank you for joining, Liminal. Look, let's see. Blah, blah, blah. Yeah, no. Hey, I mean, entropy seems to explain a lot as well. But okay, so the whole point of that is, all right, that's how we define it. All right. Now, the interesting thing is if we go to our friend CoData, so if we do CoData, let me just bring that up. Boom. Let me share with the class. All right. I look at H bar a lot. Hey. Let's just go to Planck. All right, boom. All right. So let's go to the Planck time. Okay. Right here, all right, we get a bunch of digits. Now note, 5.391, yada, 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 times 10 to the minus 44 seconds. That's a ridiculously short period of time. Okay. We have a total of 7 digits here. Okay, so we got 7 digits, but these little bars here, this is the error. What this means is in the last 2 digits, we have error of approximately 60. That would be 1 standard deviation because it could be go up by that or down. So that this could go up to like a 307, could go down to like a 1. 8, 7, something like there within one standard deviation. Okay. So that means we got confidence in like about 5 significant digits, or well, this roughly about 4.5. So the moral of the story is if you go through this, all right, so you get about 5-ish significant digits. So the Planck length. All right, we got a little bit more precision here. So we got 7 significant digits and only error of 1/8. So that could go up by 18 and the last 2 digits here, or it could go down by 18 for one standard deviation. But that means then we only still have confidence in about 5 significant digits. I'm going to skip over the Planck charge, which actually is not even listed here for some reason. That's I don't know. We'll go to mass, our next dimension that we have here on the board. I should probably actually. I know it doesn't matter right now. It's only a tiny little thing, but it's Planck mass. All right. So again, we got 7 significant digits here. And then we got 2, 4 in the last 2. So that could be 5, 8 there. That could be a 1, 0 there. Okay. So are we noticing a pattern at all? Now, if we only have these 2 about 5 significant digits, 7 with error, one might ask, it's like, well, have we measured these things? No, these come up from calculations like that. So we're using the significant digits that we know in those to help define them. Now, we'll get the Planck temperature and then I'll get to my point. Okay. So temperature, we know temperature pretty well. You get 1.4616 times 10 to the 32 Kelvin. That, my friends, is a spicy constant. It's so spicy, it would just vaporize me and I don't know, probably about a Planck time. Somewhere within that magnitude or so. Okay, but again, we've got about 5 significant digits we have confidence in. Here's a question for you, my friends. We'll go back. Speed. Speed of light in a vacuum. Okay. Here's the interesting thing. Riddle me this. This is defined. We have defined this as we have measured it. We technically have the two-way speed of light there. But for the sake of argument, the speed of light as we know it, we have measured it and we have it set and defined at 299,792,458 meters per second. I will not try to say that 5 times fast, as I think that's the first time I've actually ever successfully said, "Oh, hey, Jen, good to see you. Good to see you." No, we were just giving shout out to our friend Ludwig Voltzmann. He left us far too early. And yeah, it's good to see you. Good to see you. I miss you bashing concepts into my head. But and we got James here too. I still need to read that book. I went through, I'd watched the series. I like how the series gets you to think. I actually had started to watch the original I think it was the original Chinese version and stuff too. They jump right into it, but I haven't finished it yet. Really should read the books too. Oh, we got X2. What's going on, my man? What's going on? No, we need to catch up. See, Crypto Alchemist, he runs with Michael Perrone and some of those folks over there from was it the Alternate Propulsion Crew. I like popping into those things and just hearing about different ideas and then seeing some of the other technology that comes out there. It's just, oh man, I'd love to wrap some Tesla coils. I don't know. It just seems fun. Is it relevant? I don't know. But okay, riddle me this, my friends. Why is it if we have the speed of light defined to 9 significant digits that we only know Planck constants? There are about 5 significant digits. Okay, we have 7. We have 7, but there's error there because, okay, the speed of light, all right, the Planck length could be a little bit more or less. The Planck time could be a little bit more or less. Okay, But isn't that why we have other constants too? I put this down far too soon. I apologize. Let me share my screen again. Because, okay, you need to compare that to other things. So it's like, all right, the speed of light. All right, that's one data point. What's something else that has like length and time in it? How about h bar? Oh wow! It corrected my spelling. Thank you, Codata. All right, so we got this. We've got this defined at 10 significant digits. Wait a second. We can't try to deduce that. The whole point is, all right, if we know the speed of light to 9 significant digits, because we've literally defined it at that, and we know h bar to 10 significant digits, full disclosure, it used to be 12, but there was pretty ginormous error in the last two. I think it was like 0.60 or zero point 0.7 or something. Because when I first come out here the first time, it was still defined at 12 significant digits. And then in the 19 redefinition of SI, they locked it off the 10th digit because it's like, all right, we get confidence to here, and then the error bars are making it wonky. So for sake of consistency, they just lopped it off of it. So if we know the speed of light to 9 significant digits, and we know h bar to 10 significant digits, why don't we really have confidence in most of the Planck bases to 5? And that's going to be what we're talking about tomorrow, my friends. We're going to be talking about what interesting things may be going on at the 7th significant digit, because I believe I think it was Lord Kelvin or somebody is at least attributed with saying that in like the 1800s or so, it's like, well, it seems like all of physics has basically been solved. It's only a mere question of the 6 significant digit in numbers. Now, if things kept progressing, he may have been right at that point. However, once you start getting into the realm of about 10 to the negative 7, very interesting things start to take place. So, we're going for over an hour now, but hey, thank you all for watching, and those who may be joining us temporarily in the future. And yeah, we'll continue our discussion, and who knows, maybe next few days we'll get a few friends up here and we can have little chats. But we'll see how it goes. Until then, take care of yourselves, everyone, and peace out.